Good morning, good afternoon, good evening. I hope everyone is doing well. Just a quick update on the Bills player. Uh, there is no update. That's why I haven't went live a little bit about anything. No updates. So he's still in critical condition. He's on a ventilator. But other than that, nothing new to report. So welcome to Science and Tech. Welcome to Science and Tech Tuesday. I think that made it worse. I feel like I'm very quiet. Am I quiet or no? Maybe that will help. Everything was all messed up because I don't know if anybody paid attention, but last evening we were trying to help Hayden get everything around and played with a bunch of settings, and I don't know if I like it now. I definitely don't like that. It's too much feedback. Okay, sounds good. Thank you, Manda. So let's say hi to the people, and we'll get into it. Jonathan, what's up, buddy? Mahalo waits, my brother and co-host. Hope you're doing well. Man Bun, good morning. Greedy, good to see you. What's up, Belandris? Linda, good morning. Oh, I'm sorry to hear that. I have I think we're about to get a storm because I have like a bunch of pressure and it's driving me insane. Brain Free, good morning. Afternoon, whatever it is. Hey, Rabbit, how are you? What's up, Kaiser? It's definitely morning for you. Still. Impish, you're back. We missed you. Xcomer. I think that's a Rumble only, brother. I think that's one of those things you can't talk about. But I'd love to. And I think I got everybody. So today we are talking about the principle of least action. This one's, I'm not going to lie, difficult to well, it did go away. That was part of the problem. What's up, DA Val? So this one was very difficult to this one was very difficult to explain. I understand what it's saying, but yeah. So we'll try and get through this. Not my favorite one, I'll say that. So we start with the book, and the book says, this says essentially that things happen in the way that requires the least effort. That's easy enough. So a beam of light will travel in a straight line because that's the shortest path between 2 points. If you drop a ball, it will travel towards the center of the earth. No one is quite sure who came up with the principle of least action, but your everyday experience would probably leads you to come up with it if you thought about it for a bit. In the 18th century, though, this was a big deal. Some of the greatest names in math, such as Leonard Euler, Pierre de Fermat, Gottfried Leibniz, and Voltaire, were involved in the argument of who came up with the idea first. It was important to make these kind of statements at the time because they led to the formation of equations that describe how things move when acted on by forces. This also led to the concepts of potential and kinetic energy. See, this is why I love this book. It makes it not science brain. Hang on. Let me what's up, Maddie? Good morning. No, and so this is, I don't want to say it, but it's the only way I can think of it saying it. This is the basic version, or the, for lack of a better term, dumbed down. I hate using that phrase, but I need to come up with a different one. So this is the basic version. Once we get into the math and really looking at the principles surrounding it, that supports that theory. So 3-second thrash, which is part of this book. At the core of the modern physics is the notion that nature is thrifty in all of its actions. And the 3-minute thought. Quantum theory, which describes how things work on a subatomic scale, seems to be the one area where the principle of least action does not apply. Quantum objects can be in 2 states at once and can take multiple paths when traveling from one place to another. Richard Feynman went so far as to suggest that quantum particle will simultaneously take every possible path when making its journey. There you go. Keep it simple. If nature spun everything, doesn't that make Mother Nature the biggest map on Earth? Yeah. Yep. And brain free. That's the whole thing. Because I could go like deep end, but then people get lost in it and don't understand what I'm saying anyways. So the related theories on this one are the unification theory and Occam's razor. Yeah, quantum. I'm intentionally staying away from quantum physics because we get to it in, let's see, 1, 2, 8 weeks. So, and that's going to be a deep dive. That will be a long show. So let's find where my buttons are. Do you have that? Just Valhalla, if you wouldn't mind, can you send me that light video and like Discord, in like private Discord, so I don't have to search for it? Because I know it's in Discord. I just don't want to take time looking for it. But anyways, so here we have Scholarpedia, and this is like Wikipedia, but not garbage. I believe it was Man Bun that actually sent it. Or are you talking about the one that I showed on screen? I'll find it, Val, because I know what I'm looking for. The actual best way to tell lights are waves is use a laser and notice the ambient light given off, not actually in the beam. Scattering because of wave. Actually, Jonathan, light behaves as a wave and a particle. It behaves more quantumly than it's kind of a mix. It's kind of a mix of a quantum and a general relative state. So light is weird because photons don't have mass, hence why they can accelerate to the speed of light theoretically. Blah blah blah. So again, this is like a Wikipedia based, but it is much more. It's peer reviewed, so these are scientists and academics. It was that one. I don't know. I haven't looked yet. Yes. Thank you, sir. All right. And love you, buddy. So we get into the paper. Yeah, we'll get into the double slit too, because that's such an interesting thing. Superposition. Love superposition. The principle of least action is a basic variation of the principle of particle and continuum systems. In Hamilton's formula, a true dynamic trajectory of a system based on initial and final configuration in a specified time is found by imagining all possible trajectories that system could conceivably take. Computing the action, a functional of the trajectory for each of these trajectories, and selecting one that makes the action locally stationary, traditionally called least. True trajectories are those that have least action. So that's the scientific definition. The other one was the book definition. So this really gets into the weeds with the formulas and the predictions of position. So I'm not gonna. We'll read this first paragraph and then. There are two major versions of this action due to Hamilton and Marpudis, and two corresponding action principles. The Hamilton principle is nowadays the most used. The Hamilton action is defined as integral along with any actual or virtual conceivable or trial space-time trajectory connecting two specified space-time events. Initial event A equals equation and final event B equals an equation. I'll bring it up on the night show so you can let it fly. Again, we're not going to go through all this but this is I just had an idea. Hang on. And my drawing's terrible, so don't laugh at me, please. And yeah, dance. I stole this from you. Ooh, why is it flipping like that? What is it doing? Okay, maybe not. That wasn't fun. I have no idea why I was flipping. Um, it was weird. So I'll have to explain it to you. Or hope that I can. Let me try that one more time. I don't know why I was doing that. It's fine there. It's really weird. I don't know why my Microsoft Paint is going insane. It lost it. MS Paint lost it. I wish I had a whiteboard. Do I have a white? Let me see. Because I'd like to be able to explain this. Let's see. See if it will go over. Jonathan. Okay, so it did work. This one isn't going crazy. So this. Oh, see, I told you I can't draw. Save my life. I can't even draw a straight line. Okay, so imagine that is straight because I'm terrible at it. Unless I can. Is there like a. Oh, there's shapes. So I should be able to get it there. Oh, perfect. Okay. So this is a straight line. Absolutely. This is the path that it would most likely take, based on this principle. This is also a path that it could conceivably take because it requires the least effort. Now, I gotta go back to regular drawing because I can do this one. This is not a path that light would take, or any particle. Yeah, but conceivably it would take that path. So then, if we put a planet right here, and certainly not funny, it's just a planet. So if we put a planet there, this is where it goes into space-time because, okay, so we have straight line, and then we have, why does this hate me? Then we have another straight line, and then with space-time, it curves around a massive object. Hey, Alini. We're discussing principle of least action, and we're talking about how particles or light paths or different things interact with different things. So these would be the principle of least action. These two options. This one requires more effort because it's going in and out and bouncing around. And this is what true space-time looks like, because massive objects curve space-time and make a particle. So this is why we've harnessed and utilized this power to be able to look at distant galaxies and stuff like that. So that's my kind of, yeah. So that's my terrible take at trying to draw lines. What's up, Master Shake? Yeah, we got the whole crew in here now. We have Frylock, Meatwad, Master Shake. We're doing principle of least action. So again, this is very in-depth math, and we're not gonna go through that because I'll lose 90% of the audience. So this is a guy that draws worse than I do. No, it's Tuesdays for making you expand your knowledge base, buddy. So this guy is a worse drawer than I am, but he tries to do it. So a special lecture, almost verbatim. When I was in high school, my physics teacher's name, Mr. Bader, called me down one day after physics class and said, "You look bored. I want to tell you something interesting." Then he told me something which I found absolutely fascinating. Since then, I've always found fascinating. Every time the subject comes up, I work on it. In fact, prepare this lecture, I found myself making up more analysis on the thing. Instead of worrying about the lecture, I got involved in a new problem. The subject is this: principle of least action. See, that line is worse than mine. So this is here, there, and actual motion. And this is the forces asserted on whatever particle we're speaking of that curves it through space-time. Yeah, sort of. Yep. Yeah. Think of it as you gain knowledge and you're learning. Economics was terrible. Like, econ was a waste of time, in my opinion. But yes. Mr. Bader told me the following: suppose you have a particle in gravitational field which starts somewhere and moves to some other point by free motion. You can throw it, and it goes up and comes down. It goes from the original place to the final place in a certain amount of time. Now you try a different motion. Suppose that to get from here to there, it went as shown in this figure right here. But it got there in just the same amount of time. Then he said, if you calculate the kinetic energy at every moment on the path, take away the potential energy, and integrate it over time during the whole path, you'll find a number you'll get is bigger than that of actual motion. Anybody found? In other words, the laws of Newton could be stated and not in the form of F equals ma. Does anybody force equals mass times acceleration? You guys know that one, right? Okay, good. But in the form, the average kinetic energy less than the average potential energy is as little as possible for the path of an object going from one point to another. Let me illustrate a bit better what it means. If you take the case of a gravitational field, then if the particle has a path xt, let's take it one-dimensional for the moment. We take a trajectory that goes up and down, not sideways. Where x is the height above ground, the kinetic energy is 1/2 m. It's fine. You're competent. Okay. And the potential energy at any time is mgx. Now I take the kinetic energy minus the potential energy at every moment along the path and integrate that with respect to time from the initial time to the final time. Let's suppose that the original time, t1, we started at some height and ended at some time, t2. We are definitely ending at some other place. So this is just an overcomplicated way to find the energies, times, everything about this on this path. So big numbers. The actual motion is some kind of curve. It's a parabola. If we plot time against time, it gives a certain value for the integral, but we could imagine some other motion that went very high and came up and down in some peculiar way. Oh, I was like, what is that? We can calculate the kinetic energy minus the potential energy and integrate for such a path or for any other path we want. The miracle is that true path is one for which the integral is least. So we can predict how things are going to happen. Yeah, I need to do time travel. We're working on it. I got a response video to dance. I got to do time travel. Yeah, you need a pretty considerable mass. So okay. A lot of reading. I'm trying to, but it's interesting. At least I think so. I think we can do better on this one. I went back and forth, and so let's try this one for a minute. Because I feel like if I just keep reading complex stuff, you guys are just gonna lose me. So this is basically particles. If Lagrange were simply a shortcut to find the equations of motions, we wouldn't care about it too much. It would be a nice calculation trick, and it might have found us some use in numerical algorithms. But it would not be the bedrock of modern physics. Blah, blah, blah. We already heard all that. Shortest distance between 2 points. Using the Euler-Lagrange equations to provide all the following statements. The line, or a line, is the shortest path between 2 points in flat Euclidean space. A great circle is the shortest path between 2 points on a sphere. Yeah, that's a good way of putting it, buddy. Perfect. Well, welcome, Kendra Kate. Hope Pixelate is doing well as well. So now that we provide in the last article that the geodesic equations can be written in terms of Christoffel symbols or in terms of Lagrangian and the Euler-Lagrange equations, or Lagrange, I guess. Hey, what's up, Levy? Geodesics on a cylinder. People sometimes say that geodesics are the shortest path between 2 points on a manifold. While the shortest path on a geodesic, not all geodesics are the shortest path. To give an explicit example, say you have a cylinder. I'm not doing math this morning. Sort of. I'm sure we could figure that out. We're not doing math. We're skipping math. Snell's law and wave mechanics prove that waves naturally follow Snell's law using the method described. Oh, this is like an exercise. So this is our closest path, and it may not seem like it because you'd think, well, this one's flat, but based on all the factors, morning, just on. So we'll watch it play the animation one more time. So that's what I said. This one is, it's foundational to physics. But it's really hard to explain effectively, at least for me. This is one that I'm not great at explaining. I know the principle, and we use it all the time, but you should have the same setup as, well, in the proof that waves follow the law of reflection, there are two stationary paths made up of straight lines. One bounces off a mirror according to the law of reflection, while the other goes straight from the source to the destination. What's the blue line represent? I have no idea, honestly. I think it's some sort of prism. Yeah, it's some kind of prism or reflector. But they're not terribly clear on what it is. So this is what I drew, but mine was much poorer. So here's a real world example. So obviously, you guys know that we don't actually see, like, you don't actually see me. You see the light that's reflected off me. Correct? You guys know that? I'll take that as a yes. So we're there's no wrong answers here, buddy. You can say it. You can. You can also taste. Yes, shortly thereafter. So you're never in the position that you're actually in either, because time dilates. Kind of, but it's more of a reflection. So colors are just our sense of reflection of different spectrums of light. So obviously we can see this gentleman. here. We can also see the reflection here. So the light, this follows that principle. The light's obviously coming straight at you into your eye, but it's also bouncing off this reflection or bouncing off this medium and reflecting back to your eye. So you can, if you visualize, you can see that uh, you can see that principle where there's a bounce effect or a valley. So blah blah blah. Yeah, that's all the math. We're not going through. I'm not doing calculus this morning. That's not going to happen. So a lot of this gets really into the weeds, and I don't know that we want to be there. Jonathan, you're so funny. Certainly, Kate. It's so if we were to actually, and I think they've actually done it. That's not true, Levy. I like your thought process, but that's an incorrect statement. We are the real ones. So anyways, where was I at? Yeah, so I think they have a simulation of what the world actually looks like. And maybe I'll make a note and I'll look for that. I'll ask a friend of mine and get something. Exactly, Jonathan. You got it. Northwest Ohio. It's insane. Like it's really hard to imagine that we do all that to make it better. So we really are. We're spectacular humans. So spectacular species that can. Our body does some crazy stuff. But Jonathan, here. Well, where is my? I'll prove it to you guys once and for all where Australia is. It's right there, Northwest Ohio. Everybody see that? That's actual size Australia. And it's right there in Northwest Ohio. So Oz is like an hour and a half from me. So we solved that conundrum too. So we're just breaking barriers here today. So you may have heard of the phrase of principle of least action. While objects take paths that do minimize action in many circumstances, often take paths that do not minimize action. While no object ever takes a path that maximizes action. Blah, blah. You can always add wiggles in the path to increase the action. Objects take paths that neither minimize nor maximize the action. If you want to know more, read this paper. No, thank you. Which is pretty clear as papers go. It was a pretty good paper. I read it, but in a summary, the action is minimized in short time frames. Uh, so particles are lazy. Right. Yep, Maddie. Uh, this is the quick summary, and then there's a video that maybe we'll watch. Particles are lazy. They want to they want to do the least work to get to the destination. Sometimes they take a wrong turn, but they would never make it harder on themselves, particularly. So they're not going to, if they can take a car and drive a mile, let's say. So they can take a car and drive straight down the road, one road, and make a right turn. Okay. And straight down that road. So we have that triangle type. Or they can just say to hell with it, and they can just drive across the people's lawns and do a straight line. But they're not going to they're not going to make 30 or 40 turns, go around multiple blocks, and ride a bicycle when they could drive. Does that make sense? Maybe. All right, Greedy. Take care, buddy. But so it's not going to take there's some form of indifference because they're not they're obviously not intelligent. I mean, these particles don't have a brain, so they're going to do what's the least required energy, but sometimes it's not the path that requires the least energy, but it's the path that is easiest at the time. Yep, that works. We're not doing Gauss principle of least constraint. We're not doing math. I thought this one was that's going to get too in the weeds. Read a couple more of these and then what's up, Isabel? Fermat's principle. What works for the equations of motions with a massive object, which I've proven in the previous article, why would Hamilton say that we could write a Lagrange for everything? Let's talk about Fermat's principle, the first inspiration of Hamilton's principle. Fermat's principle was the first modern statement to say X takes path that does Y. In physics, stating the light takes the path of least interest or least time between 2 points. This principle is a generation of Hero Alexandria's earlier principle that noted that light takes the path of least length, would imply the law of reflection shown below. Physics is the mass of never ending. Like, oh, Sean, we're not getting into that. Not today, sir. can do soothing music. I like this one the best. Hollywood premiere lights. Sorry, I was catching up on different chats. Here's things like uniform media and reflection. Let's say that we're in a medium where light travels at constant speed, which we're not. We're in a fluid. In that case, the path of shortest time is the path of shortest distance, which is this line, so light travels in straight lines. If we have any reflections, you could still get a straight line if you reflect all the destinations correctly. For some basic geometry, vertical angles and symmetrical triangles, we can conclude that the angle of incidence must equal the angle of reflection. Snell's law. We can also use Fermat's principle to derive Snell's law. Say that we have a light source, an observer, and two different media. That's what that was. This wasn't a refraction. This was a different media. So I apologize. I could have read that. So that earlier one with the lines and the yellow lines. So this would be the vacuum of space, and this would be Earth's atmosphere. Although the straight line distance is the minimum distance, it's not the path that takes the least amount of time. Let's say that Let's say that the speed of light in one medium is c over n1, and the speed of light in the other medium is c over n2. We call n1 and n2 indices of refraction. Furthermore, let's label our source position x1, y1, our destination position x2, y2, and the point where light hits the boundary between media x, y. So then this is a basic math problem. I'm not doing it on screen because I don't feel like it, but it was pretty basic in the world of mathematics. Blah, blah, blah. So that's just how we got to it, and we can predict what path is the best. You're starting to get it? Fantastic. No, we're not going into that. I don't want to do math. No, we're not getting into quantum mechanics either. String theory is disproven. Okay, we'll go into stationary action, and then Jonathan, that was basic. What are you talking about? No, Jonathan. It's nice that you can reflare. Oh, I gotta check Rumble too. Okay. Shade's driving, but smash the plushie and listening. Fantastic, Shade. Yeah, that's not gonna happen. Yeah, it's string theory unraveled. Ha ha ha. Science joke. I know that was terrible, but yeah, the they disproved some of the basic fundamental particles of string theory. Jonathan, technically I did, because my quantum feet are in superposition, so they're everywhere and nowhere. Math's fun. We could do math at some point. Why does stationary action work? It's nice that you can rephrase all systems in terms of finding paths that make the Lagrangian stationary, blah, blah. But it begs the question, why does nature take paths that make Lagrangian stationary? Maybe it's just a coincidence that the Lagrange equations show up in both contexts of making something stationary and the equations of motion. Maybe the Euler-Lagrange equations are so general that you can make any set of equations from them with the right functional. It sure would be interesting if there were some natural phenomena for which the principle of least action was an emergent phenomena. Uh, 2 plus 2 is 7.5, Libby. Exactly. %. Oh, that was worse than mine, man bun. Jonathan, I love you. For a great, God, I can't even read it. For a great low rate you can get online, go to the general and save some time. Okay, we're done with that. So, that's a pretty picture. We can show that the waves follow the principle of stationary action. We've already proven that massive particles follow the principle of stationary action in the previous article. But waves are traveling disturbances. They don't have local position, they don't have mass. Although matter waves exist, the wave itself does not have any mass. And they don't seem to be made of any underlying object that we can exploit. Instead, we're going to prove 3 facts. If waves are allowed to move at constant speeds, they appear to travel in straight lines. If waves bounce off surfaces, they follow the law of reflection. If waves speed up or slow down, they follow Snell's law. So we're going to try and put it into it. But, yes. Two plus 2 only equals fish if it's on a Thursday. By proving that waves follow these facts, will effectively prove that waves follow the principle of stationary action. If you're unfamiliar with wave mechanics, check out No, We're Not Doing That. I'll do my best. Waves are fascinating and often overlooked. I wrote this section specifically about light since it was part of the next article, but I moved this section to this article since I felt it was more appropriate here. If it helps, you can think of wave sources as a light source, the wave reflector as a mirror, and the change of speed as a refraction. That's a funny one. The argument is simple. If you have a point source for a wave, it emits the wave in all directions. To all observers, the wave seems to come straight from the point source. To the image below, I'm graphing the wavefront, which you can imagine occurring at one of the peaks of the wave. Ah, no, Libby. Furthermore, if you know how bright the wave was at any other point, you can use the inverse square law to figure out the distance between the observer and the source. Somebody needs to call him and tell him I need to be a sponsor. They need to be a sponsor. They only get one free. You guys know how to do inverse square law, right? We're good at math, maybe.
What'd you just ask? An inverse what?
Square.
Yeah, everybody knows how to do that, bro. Duh.
Shut up.
I don't even know what an inverse square is. What's up, everybody? How y'all doing?
We're kind of going through the different sections. So not necessarily space, but
Hey,
so
Pixel.
pixelated. Thanks for sending your buddy. You really don't know inverse square?
I don't think so. It's not ringing a bell.
Intensity equals 1 divided by d squared.
Nope.
Okay. Let's
Keep in mind, the highest math class I took was Algebra 2, I think.
should be an algebra thing. I don't know. We'll just share it real quick. So this is inverse square law. So. They've accepted you as one of their own. Proof is one of the most important proofs for understanding quantum mechanics and Hamilton's principle. You can see the qualitative discussion in this video. No, Science Asylum is a good video, but we're going to do a quantitative proof for the example. Say we have a point source, a wave reflector, and a point observer. The source is at the point 0h1 and the observer is at the point LH2. Play graphic? I guess it's not going to. Since we're working with a spherical wave, the wave will touch all parts of the mirror. By Huygens' principle, which is justified in my previous article, the wave equation, we can consider, there it is, at any point the wave touches to be a dipole source for pointing in that direction of a wave propagation. In the case of the mirror, each dipole points away from the mirror, creating hemispherical waves at each point of the mirror. Each of these hemispherical waves will reach the observer.
That makes sense.
Are you being a jerk, or do you really?
No, that makes sense. Like if somebody's standing in front of a mirror, you're going to see different angles depending on whether or not you're viewing it from the left or right side of that person.
Right, and this is basically saying that we can not only measure, but we can predict the space in which every light source hits that observer.
Yeah.
Okay. You might be thinking that we have a problem because it looks like the waves can come from any spot on the mirror, meaning the whole mirror should be bright. We can solve this problem by introducing several corrections. She's been gone for like 3 days, pixelated. Oh, don't worry. We'll make up for it tonight. Waves follow the inverse square law. We should expect the intensity power over the area to be greater the closer the wavefront is to the wavefront that reaches the point first. So this is where inverse square comes in. Jonathan identifies as a goat, legitimately. Furthermore, it means that the wave at the destination itself won't be an infinite magnitude. Again, no math. We're not doing Pythagorean theorem or other maths.
I know that one.
Do you? Okay.
A squared plus b squared equals c squared.
Yep.
I can find the length of the right triangle sides.
You want to do trig?
Don't know trig, bro.
You don't know this? Okay. This is actually...
The only thing I know is, well, I don't know it, but tan. I know it, like tan, sine, and cosine.
Okay. Yeah, they're all Jonathan's children, kids. They're called kids, right? Baby goats? Yeah.
Yes.
So this is basically we're not going to go into that math. I had to do math this morning. I don't want to do more. Most standard demonstrations of Snell's law in early physics actually use wave optics to demonstrate Snell's law instead of variational principle. So a variant of this image should be familiar if you've taken a few physics classes. So it essentially says it's coming off the wave. This is the most efficient, but all of these other systems are working. Because like you were talking about with the Big Bang, like there's nothing for it to interact with here. So it should just come out as a normal circle that uses an inverse square and gets larger as it goes. When it starts interacting with the atmosphere, then it collapses on itself and makes the wave. This is Pong. I wish.
This is what?
I said I wish this was Pong, the game.
Oh. Yeah, I'm a little sore today, buddy.
Well, that's good.
Yeah.
Means you worked hard.
Yeah.
We're not going over that. I think we're self-promotion. Fantastic. This is... I'm going to have to bring it up full screen. This is that paper. If anybody actually wants to read it, just reach out to me. I have it. So... I don't know if I can actually... I don't know if I can drop that in... Let me see. Maybe there's a new Discord tab on its way.
Calm your Latin.
I wish I spoke Latin. That would be so cool. And the only reason I would want to do it would be to brag about it. I speak Latin.
Just a flex.
Yeah. I speak Latin, you don't? Why don't you speak Latin? Hang on. No new goats?
Nope, not yet. Not yet. I think we're still within about 2 weeks though.
About 2 weeks, you said? Okay.
So I think we're getting pretty close.
Okay, so we have the science and math, and let's see if it actually goes in.
I just went up there and checked on them. Moms are looking fat, but they're still looking fat.
Good deal. Do they get less fat when they...
After they spit the kids out, yeah, their bellies deflate quite a bit.
I know, but I was talking about, do they get like less fat before they have babies?
No.
Okay.
goats carry their kids on one side of their body, so you can like feel them while they're in there and stuff.
Oh,
See 'em
okay.
moving around. It's pretty neat.
Gotcha. So yeah, I dropped that. Oh wait, I probably shouldn't put that in. So I put it in Discord, the paper. It's actually a pretty easy read, if you're sciencey at all. And there's a science and math channel in Discord now. So, but that is basically it for the theory of the principle of least action. Do you know the genders of your goats? I assume she means babies. Mr. Holla.
No, not to be born. I don't have like ultrasounds and stuff. I'm not that fancy, y'all.
Do they have more male or females, or is there like a probability, or is it just 50-50? And
It'll just be about 50-50.
Okay.
Should be. My first year though, I had 7 boys and 1 girl.
Wow.
Yeah.
Okay. But you got rid of all the boys, sold the boys, or? Yeah. Okay.
Yeah. I was trying to grow the herd, right? So I was like, okay, we'll sell some of the boys and keep all the girls, and I only got 1 first year.
Bake it. Yeah, Jonathan, he sells some of them. I mean, you're here, so you can talk about it, but if you want.
Yeah, I do. I currently sell some of the boys. But I want to start sending a couple to slaughter a year. Getting some meat.
No, he likes to grow goats because then he can have more goats.
Exactly.
Yep.
Oh, it's kind of neat though. Like I've sold some
What's
of the
up,
boys.
Flux?
Hey Flux, how you doing? I've sold some of the boys to like, I try to sell them to farmers more than butchers or whatever, more than people taking them to auctions, I guess rather.
Okay.
But yeah, that's a big thing. People will try to scoop goats up and then sell them in auction and make money that way.
Okay.
I don't know how I feel about it, but anyway. So a lot of these people that I've sold goats to are getting into goats like I did, right? So they're starting a herd or adding to a herd or whatever. So a lot of these people I'm still in touch with, and I get to see these bucks grow. It's pretty neat.
That's cool.
Yeah, it's pretty cool.
Flux is supposed to be working, but she's sneaking out and watching Principle of Least Action. But yeah, so that's kind of a breakdown of it. And like I said, it's an interesting principle to get into. It's not complex, but science makes it much more complex than necessary.
Kind of reminds me of electricity flow a little bit.
Kind of. What's up, Miss Amanda? I just saw you in there. There are some scientists aren't great at, and I've said this before, communicating English. They are better at communicating nerd, and that's a language I speak both languages and can translate, so I'm helpful. But yeah, and one of the things, so to tie it back into it, one of the things that just blows my mind is we can have light on a dark night that comes from 10 billion years in the past and has snaked its way through the entire universe and just get sucked up by your eye. Like, doesn't it seem like such a waste? Like, it just...
No.
It's so beautiful, and so, like, to know that particle flew through space.
Yeah, it's not a waste by any means. It's an amazing thing that we get to discover and observe every day.
Right. Well, I think we waste it because we don't realize it. But go into the night sky, look at a star. That light's coming from millions, if not billions, of years ago.
That star's likely already dead.
Could be. Yep.
Or potentially, not likely.
Potentially, yeah. Well, that's like... I think it's not. Is it?
What?
It escaped me. So anyways, there's a star. I want to say it's Betelgeuse, but my mind went blank.
I love that there's a star named Betelgeuse. That makes me so happy.
Yeah, it's spelled weird too. Weird.
I saw that when you were typing it in the other day.
That's how it's spelled. So
agreed.
Yeah, no, and that's DB. That's one that's a hard question. So because it's expanding at different rates, for whatever reason. So, but back to and that's what I'm trying to say is things are beautiful, and go look at the stars at night, and
it's all pretty amazing.
You can see light that has made an immense journey, an enormous journey from 10 billion years ago. And it decided to go into your eye. Like, it's one of those things that if you stop and think about it. But anyways, the thing with Betelgeuse for you, Val, is he's here. The thing with that is it could have already gone supernova, and we wouldn't know for a long time. And if it goes supernova, like, it would be bad news for us. Like, we wouldn't it wouldn't be an extinction level event, but we would definitely feel effects, altered communications, maybe some satellite interruptions. So
is it close enough that it would, like, potentially raise the temperature?
Probably not. It would probably be EM radiation. That would be the highest. We might get a slight bump, but nothing consistent for a long period. So
you broke him. He's not in the studio. He's just gone. Look what you did. You killed Mighty.
All right, I'm back.
What the hell?
You made me so angry that I left. No, I pushed the... Apparently, on my gamer mouse, I have a button that can make me leave the studio.
Oh, that's neat.
Yeah.
Yeah.
That's fun. Yeah, Beetlejuice got me. So I think, Devout, I think I am anti-dark matter. I think it is cheap. I think it is
a cop-out.
A cop-out, an excuse to, it's got to be dark matter. Well, that doesn't help. So that doesn't help anything. Yeah, I can make up magical stuff too. So I am not a fan of dark matter, and they haven't found any. So we have Kaiser. Now I'm all freaked out that I'm going to hit that button again. It's the one So it's right on my thumb. So if I slide my thumb up, it's that button. So I'm gonna have to change that.
I would maybe switch that hotkey. I think Neil deGrasse Tyson was talking about evidence of dark matter, though.
Oh, everybody talks about it, but I haven't seen anything in a paper yet. I mean, I'm biased. I'm biased as hell, but so if you guys are ever, sorry, catching back up. If you guys are ever in northern Michigan, and this is right outside of Mackinac City, it is one of the few. It's
statuesque.
Huh?
Hi, statuesque.
Hey, statuesque, what's up? This is one of the few parks, International Dark Sky Parks. It is beautiful. You're not allowed to have any lights or anything like that.
Really?
It's gorgeous, and you can see this is what the normal sky looks like. I have some pictures from there. I just don't know where they're at, so maybe at some point. But yeah, it's right outside Mackinac City, to the west of, the downtown and the fudge shops and the tourist area. So yeah, zero light pollution. It's fantastic.
In Hawaii, when you get up in the some of the peaks in Hawaii, it gets pretty awesome.
Yeah,
On
I can imagine.
Different islands, especially.
Crystal, you may ask. I don't know that I'm going to answer it because that's like a whole show topic, but I can break it down really quickly. So dark matter is a theoretical particle that they believe is holding the universe together. Antimatter is just a flipped charge. And we've actually made antimatter. So antimatter, I do believe in, and it does exist. Dark matter is this majestic, unprincipled thing that they're using to unify different theories, but has no practical bearing. So it's just dark matter is whatever they want it to be to make their theory fit. Antimatter is just the opposite flip of pole of a particle. And when it comes in, when matter and antimatter come into contact, they annihilate and release immense amount of energy. So oh, did he, Xcomer? So who's going to be the speaker? The slew? Huh. I'll have to look at that. So in part, they were looking for fundamental building blocks, and one of the things they did collect a very small amount of antimatter. Antimatter is unstable in our world because we have matter. Yeah, re-election. Okay. Yes. Yep. So it's flipped. So it's a negative charge. All right. Well, I am going to wrap it up here because I have a couple more things to do and I have to get back to Ick. So, thanks everybody for stopping by. And next week we have laws of motion. So some more physics. Fun.
That will be fun.
I could. I don't know if I have time, buddy. Got to do the day job too. So if I get a minute, I'll think about it, but full HD and on olives. Girl, you got to put those olives down. Those are dangerous. Oh,
Olives
no.
are amazing. Love me some black olives.
Really? I'm not an olive person.
Love black olives. Oh, look at you guys.
I appreciate it. So
For real. Kendra, come back. We're here most days.
yeah, Monday through Friday noon, and then 8:30 night shows every day, but Monday and Wednesday. So
And night shows get spicy.
spicy meatballs.
I made Hayden private his thing last night. I didn't make him; he did it, but because of something I did.
I appreciate it. That's where we want to be. We want to make it fun. So Valhalla did get a haircut,
I did. Check it out.
and he looks gorgeous.
I did a pretty good job.
But all right, guys. Well, thank you so much. Hit that like on your way out. Subscribe if you haven't, and we will see you at 8:30 tonight.
Yes.
Have a good one.
Later, y'all.